Well, hello 535 people. This is Dr. Q Schubert. Just finished the orthogonality one. Now we're going to move on to projections. Now when we deal with projections, what we want to do is have something, and we're going to call it, say, some P that's a matrix that takes, something. Let's get a kind of picture here. Let's say I've got, some vector A and I've got some vector B. What we want with the projector is the idea of, you got a sun directly overhead and that it casts a shadow, and that shadow we want here to be the projection of B onto A, right, which we write P sub A of B. P sub A means projection onto A of the B, and we want to do this by some multiplication, so we want to make something that meets this requirement. Now that shadow from it being directly overhead tells you that I've got a little 90-degree angle. This is why I wanted to start off with orthogonal ideas first. So that kind of gives you the idea of where that comes in. Now this, if you look at it, gives us this nice lovely idea of a triangle. So let's pick our triangle. It's not just any old triangle, it's an orthogonal triangle. And we've got something over here that has length of B. Now if I asked you, if this is length of B, how long is this side? Well, most people would come in and go, there's some angle over here, theta, so this must be B cosine of theta. Now, once you make that realization, that means the length of projection of A of B has to be B cosine theta. That's what we would like it to be. Now, if that's what it is, well, we want it to be multiplication. You've already got B right there. That means that this projection of A, in some sense, has to handle this cosine of theta. Now the cosine of theta is handled by the fact that you have an angle between these two vectors. The second you think about angle between two vectors, you go, angle between two vectors, that's an inner product. So that means that this projection of A to B, to get that measured angle, it's got to, in some sense, do something or other, right, times this A onto B. Now, I shouldn't, whatever, we have some squiggle thing, right? There's some unknown thing over here. And that right here, A transpose B, well, that's going to give you the idea of the norm of A times the norm of B times the cosine of the angle. Now when I did this, I said this is the length. Well, truly, if it's the length, it's really the norm of B. So I've got this in using matrix terms. So we go, oh wow, I've already got norm of B times cosine theta. The only thing I'm missing is norm of A, but I want to get rid of it. If I want to get rid of it, but A transpose B has it, I've got to divide it out. So if I take A transpose B divided by norm of A, it removes it out. Now I've got norm B times cosine theta. That's exactly what I was looking for. Okay? So now I've got this idea of, I've got the correct scaling factor to get the length right. Alright, so we just said, take a look at the triangle. It's length of B on this side. Alright, if it's a shadow coming down, there's an angle. We got this. And then we want to make something that would give me the correct length. Now a vector is not just a length, a vector is a length in a particular direction. And the direction that we want to go is this should now be pointing in the direction of A. So if I take the length that I want, which is just a scalar, and I multiply it by the direction I want, then I will get a correct vector. But this direction has some scaling because A is not necessarily length 1. So I'd better get rid of the length of A. Well, you get rid of the length of A by normalizing. So now what I've got is, in order to accomplish the correct length, I had to have a unit length direction times the correct length I wanted. And the correct length I wanted was here, which we figured out by using our triangles in trigonometry, in a particular direction that was a unit length direction. Well, this then has to be the projection of B into A. Right? there's B, there's B. So projection of A must be what is left over. So that tells you that the projection onto A must be A times A transpose divided by the norm of A squared. That gives us our first lovely little result. If I want to project onto a vector, A, I have A times A transpose, and then I want to divide that by the norm of A squared. Awesome. So now we have a way of calculating a projection. Now let's consider some things like that. What would happen, right? So I've got here, I'll try to position this so it's a little better. I've put myself under the light in the room. All right, so hopefully you can see this little shadow underneath my pen. Now I've got my pen at an angle, so you can see my shadow. Now what would, or shadow of the pen, what would happen if I took a piece of paper down here and I cut it out, right? And I laid it on the piece of paper, or laid it on my whiteboard here. That piece of paper would be the exact shape of my shadow. What would the shadow of my shadow look like? Right? Well, the shadow of my shadow is the shadow of the original. Right? So the shadow of the shadow is the shadow. Now that probably sounds a little silly and people go, wow, that's a tongue twister and whatever else. But just think of the idea. If I had the cutout of that, that is the shape of the shadow, the area underneath the paper, when laid down on this whiteboard, would be dark on the bottom. That's the shadow of the shadow. Now, you go, why do I care about that? Well, we're doing a multiplication. Right? If this pen was my B vector, right, then we're saying that PA times B, that's the projection into A. And we want to stay in A. Well, what would happen if I projected it a second time? It is possible I could end up doing a second multiplication in one of my algorithms. But the projection, the shadow of the shadow, should stay in my whiteboard. We don't want it to flip out of the whiteboard. That would be horrible. So we need the projection, right? The shadow, right? Projection of the projection of B had better be the projection of B. But this has to apply for every B that is out there. If this is true for every single B, then it must be true that this is the case. But PA times PA is PA squared. So we get the projection of A squared has to equal projection of A. Now this is a neat little property about projections. This particular property is called idempotent. You don't have to memorize that one, but if you want to look it up in Wikipedia or something like that, it is idempotent, right? So, and it's got kind of a neat thing. If you're wondering, ident kind of gives this idea of one. Let me do just a little diversion on this. And I'm getting tired of writing P sub A, so I'm just going to call it P at the moment. So if you think about it, right, if I've got P squared equals P, just for a scalar at the moment. Right? So if P is a scalar and this is true, what values of P does this work for? If I put in 1 squared equals 1. So trivially this will work for P equals 1. But what if I took 0 squared, right? 0 times 0 is still equals 0. It works for 0. That don't work for anything else. So, if you actually want to plot this, this is just the equation, the roots of P squared minus P equals 0, and it has two roots. It has a root at 1, and it has a root at 0, and you have a parabola. And so that's the only two spots it hits, so it couldn't be the only two solutions, because it's the two roots, and away you go. So it has a root at 1 and a root at 0. So, it turns out once we go to matrices, that this same idea of having 1 and 0 in the system still holds true. So this becomes kind of a neat little property about projectors. But we've got kind of the fundamental thing of what a projector is. A projector has to have it true that P squared equals P, and now, P can be whatever. It could be a matrix and so on and so forth. It could be a scalar. If you're in a scalar world, it's either 1 or 0 at that point. Alright, so what can we do with this idea of a projector? Well, what we can do is actually solve an awful lot of problems. We want to be able to check to see that this happens, and we often want to project things in. It'll turn out that this idea of a projector is the basic idea that's going to come on behind our orthogonalization technique that we're going to do. We're going to make orthogonal projectors to solve the least squares problem. And that's going to turn out to be numerically a really good thing to do. It's a little bit difficult for a human being, but it's beautiful for a computer. So let's take a look. We now have this property here that we would like it to be. The shadow of the shadow equals the shadow. Let's see if that works for the particular projector that we had talked about before, which was what happens when P is equal to, our P sub A in particular, was A times A transpose divided by the norm of A squared. Where I just kind of combine them together on the bottom. And remember, norm of A is a scalar, so I do have division for scalars. Alright, so if this is true, I should be able to take the projection of A squared. Well, that's got to be A transpose over norm of A squared times A transpose over norm of A squared. Now, that means I'm something over norm of A to the fourth. And the top is A transpose, A transpose. Now, notice right here in the middle, though, I've got A transpose A. Just as a little side note, A transpose times A was the norm of A squared. So right here, smack in the middle, I have the norm of A squared. That means, let me make sure I've got a little bit of room here. Not a lot, I better make sure I write very thin. That means the top is norm of A squared over norm A to the fourth. That fit not perfectly. We will make it slight addition. Sorry about that. Alright, so now you can hopefully see. Alright, we've got norm of A squared divided by norm of A to the fourth. And then I still have left over on the outside A transpose. Norm of A squared over norm of A to the fourth. This one cancels that out and just subtracts 2 off it. So I have A times A transpose divided by norm of A squared. But that was P of A. So that means P of A squared must equal P of A. So it indeed does satisfy the idempotent property that's going on, which means that this is a projector. This is a very important idea to us. Now, in addition to this, we showed that we picked this to be orthogonal. Right? So this is both something that is going to give us orthogonality as it goes on, because all you have to do is take a look. If I had a second projector on this one, I could pick a vector that was normal to it, and it's going to give me 0, because I'd get A transpose times whatever the thing it's orthogonal to. We have that built-in inner product that we designed to, so it'll drop out 0. So anything that's 90 degrees off from it will drop out 0, and its unit length. So this is an orthogonal projector. That's kind of a nice little feature. So not only do we have a projector, but we have a particularly nice projector called an orthogonal projector, which also gives us unit length. That's beautiful, right? We've got our orthogonal projector, and this is actually what we're going to do when we form our QR projections. We're going to make a Q, which is an orthogonal projector in some sense, so that we can now build up a solution that is numerically stable. And this will extend nicely into a lot of special cases that goes on, and we can use this to do it one column at a time. We can do it, a whole bunch of elements at a time. We can do all kinds of neat things, which opens up the ability to parallelize things and things of that sort. And it's kind of commentary at the end. I'm not expecting you're absorbing it all, but I am expecting that it's kind of sinking in some general ideas to you. The big thing to walk away from here is more this idea that I can do this, squaring, and I keep it out. Now, I mentioned to you that I should have something that's orthogonal to this. How can I find such a strange piece, a vector that is orthogonal to this? Let's take a look at what we can do for this. All right. What we're going to do to call an orthogonal projection, right? Orthogonal is the perp space. Right, so we just say it's perpendicular to it, and that's the symbol for perpendicular. So if I want some projection onto that's perpendicular to A, right, that's what that means, projection onto A perp, right? We can also do it this way, projection onto A perp. Right? If I took that times the projection onto A, I would expect, right, if I took the shadow of my vector down here onto the space perpendicular, well, that's the vertical part here. If I took the length of my shadow in the vertical direction, it's infinitely thin. It had better be 0, or the 0 vector that goes on. Now we go, oh, okay, so that's kind of a cool sounding idea, but how do I find such a thing? And now, it turns out there's a very nice, easy way to find an orthogonal projection on here. And we can use that idempotent property to help us out. Now, consider for a second the matrix I minus P. Okay? So if I have I minus P, what would happen if I multiplied it by P? Well, distributive property would give me P and minus P times P, which is P squared. We've already showed P squared equals P. So I've got P minus P. So that's got to be equal to 0. So that means that I minus P and P have to, when I take their inner product together, they have to give me 0. Now these are matrices, so I'm cool off this. Right? And this actually nicely takes care of stuff. Right? I found out, wow, amazingly enough, this is equal to 0. Now in particular, you go, well, technically I should have a transpose here. But identity is symmetric and P is symmetric. So we not only actually have that P squared equals P, we have P squared equals P transpose. And this last one is an important property I kind of skipped over for simplicity, but maybe I should show this one as well. This is part of that orthogonality thing that we were dealing with. Let's just show that our particular one, right, the projector we've been dealing with, PA, which is equal to A transpose over norm of A squared, has this property that PA equals P transpose. So we now want to transpose this. When you transpose them, you reverse their order. And then you transpose each of the individual elements. The transpose of the transpose is the original matrix. So you get A transpose over norm of A squared. But that is exactly what PA is. So you have PA transpose equals PA. That's kind of a trivial result here for this one, but it's important to see that that is true. So we've got P squared equals P transpose. Nice easy case, so that means it's a symmetric matrix. That's beautiful. This becomes very important for physicists out there and for anybody who simulates physics. Our transpose have the symmetry property, and remember, symmetry is huge in physics. This is the whole idea from which they're actually to derive that there must be things like Higgs bosons and stuff actually comes from the fact of a symmetry property. That's a little bit beyond the scope of this course, but it is kind of interesting to see that this all ties in. This is kind of basic ideas on which our universe revolves off of. All right, so we've got this cool properties, right? Identity matrix, it's 1 on the main diagonal, 0 everybody else. It's trivially symmetric. So we now have that I minus P is a symmetric matrix, right? Which means that this has to equal, Right? The transpose of it must equal itself, and that's trivial because if you just take each individual one, they're both symmetric, so their difference is symmetric. Now, does this hold such that I minus p quantity squared is equal to I minus p? If so, it's a projection itself, and we've shown that its inner product with p is 0. That would make this the projection onto the orthogonal space. So let's try it out. I minus p times I minus p, and now we're going to just multiply through. I times I gives me I squared. That's 1 squared, so it just equals itself back. And then I get the cross terms. I get I times minus p, right? And I get minus p times I, and then I get minus p times minus p, which is plus p squared, but p squared is equal to p. Minus p plus p cancels out, so I minus p quantity squared is equal to I minus p. So that actually means that I have now discovered that I minus p is orthogonal to p, and both p and I minus p are idempotent, and they are themselves symmetric. So that gives me this nice case that both of these satisfy our projection properties. And since they're orthogonal to each other, this is one space that I'm going to, and I minus p gives me the space pi over 2 radians off, or 90 degrees if you still like dealing with it. So this is the space, and that's the orthogonal space, which means p perp equals I minus p. So now we've discovered a projection onto a space and a projection onto a space that's orthogonal to it. That's a really nice thing, and it's really easy to calculate. We like these type of features, so that gives us some neat properties. This becomes very important and helpful to us when we start doing things like actually calculating spaces for these various transforms and projectors to calculate the orthogonal projections, and therefore being able to calculate how to zero out a bunch of stuff. So that's why we needed these. These are some preliminary results. From this we can actually develop things like our householder reflectors and things of that sort. So, but that's going to be a topic for another time. So you should walk away with hopefully some idea of understanding how to get this orthogonal thing, or at least what it is. When we deal with it and we have to find it, we can get them. But remember, we were able to get p by taking whatever vector we wanted, and we can square them, or in some sense inner product them, a times a transpose, and then having normalized a, and so then this one must be I minus that. And from there we can build up all the stuff that we need. So now you have the mathematical background necessary to understand householder's QR, which is in some sense the kind of harder QR for a human to understand, which actually means it's going to end up being pretty nice to implement. So for dense matrices, householder's QR actually dominates, and that's what we will get on to next. So have a good day, and I'll see you in a video in a few secs.